Hello students of statics, this is Dr. Dan Baker with a lecture today looking at an example of a wrench where we can basically use our knowledge of this wrench to figure out the amount of moment caused by a force applied to this wrench. So I've got a number of different things I'm going to hopefully help describe to you in this example, not just the computations, but kind of the physical meaning of not only what is a moment but a line, but also how we can apply that concept to a wrench itself. So what we have is we can imagine that there's going to be a bolt here at point A, and that from O up to A is like the extension on a socket wrench, and then from A to B is the wrench handle itself. I'm applying a vertical force here at point B. I tried to create a little physical model of the same thing here, so we can think that our origin point right here, this would be point O, this corner here would be point A, and then when the hand is applied over here and this force is coming down through my hand, this is going to be point B. Like I said, where that force is coming through. Okay, so that's what we're looking at, and you could think that maybe we're trying to loosen up that bolt, and it lies upon a line that is 30 degrees from horizontal. Okay, so from here up to here is 30 degrees. So hopefully that gives you some physical context of what we're talking about. And of course, the moment that we want to remove that bolt is along line OA. Any other moment that exists from us pushing down here at point B is not the moment we're looking for. It'll still exist, but we want to know how much moment we're getting here along line OA, and so we'll compute that. To give us a little bit even better view of this, let's go ahead and take a look at this interactive so you can kind of see the spatial context of this system. So here is that wrench, here is our axis system, and we can kind of look at it down from the end of the wrench. You can see that AB is parallel to the x-axis. Here's that 30-degree angle. Now the dimensions, we'll add them to this system overall, but we're going to say this extension here is 7 inches, and then it's 12 inches from A over to B. And once again, B is parallel to the z-axis. It's actually in the negative z direction. We'll come back to this after we find our answer. All right, so the things that we're solving for is we want to find the vector components of this force around point O. Okay, so we're going to do that first as a separate step, basically a moment about a point. And then we're also going to find the moment magnitude of that same force about line OA, right, which is the extension going from O up to A. All right, so the length here from O to A is 7 inches, and then the length from A to B is a total of 12 inches, or 1 foot. So as we think about what moment arm we want to use for part 1, we typically want to go from the point of interest to the line of action of the force. We technically could pick one of two lines. One of those would be, probably the most obvious one, is R of OB, right, from point O to point B. So that would look like this. Now, technically, we could get the exact same answer if we picked a different position vector, and that position vector went from O to BXY. Sorry for the double subscript there, but so we said that we had to pick from our point of interest to a point on the line of action of this force, right? And so BXY is basically the X and Y components of point B, where the Z value would be 0. I'm going to go ahead and use ROB. So let's go ahead and write this vector out before we get into actually using it. So its components are going to be related to two different things. One of them is going to be the distance from O to A. And so as we look at the components, that will be in the Y and the Z components. They're all three going to be positive. So let's go look at the Y component. That's going to be 7 cosine of 30, right? This adjacent side here to here. And then we have that vertical component as the Z, so that will be 7 sine of 30. And then in the X direction, it's going to be 12. Okay, and so those are all in values of inches. Our force vector F is equal to 0, 0, negative 40, because we're pushing downward with 40 pounds. And so we have those two vectors. Next up, we can take a cross product of those vectors and say that our moment about point O is equal to the determinant using straight sides, my unit vectors across the top because I am taking the cross product. And so here's my R vector, 12. 7 cosine 30 is 6.06. 7 sine 30 is 3.5. And the force vector 0, 0, negative 40. So however you'd want to take this moment. Now realize that this is a three-dimensional moment. Because it's a three-dimensional moment, not all of the moment is going to be in the k-hat. We could have other components. So I'm going to repeat those first two columns. So I hat and j hat, 12, 6.06, and 0, and 0. And so if I know that my positive slopes are going this way, there's an I hat that's non-zero, that j hat is 0, that k hat happens to be 0. And then my negative, I have a non-zero j hat, and then I have a 0 and a 0. So the only two terms that will be non-zero come out of this slope right here and this slope over here. I just labeled those as the positive negative because the positive slant and the negative slant to find those values. And so computing this determinant, we find that there are components for a moment about point O as a vector, which are going to be negative 242 in the I hat. And I get the negative basically just of 40 times 6.06. And then in the j hat, I have 12 times negative 40, but then I take the negative of that whole thing, and this becomes a positive 480 in the j hat. And the units on this are going to be the product of the units of the length and the force, so this is going to be inch pounds. Okay, so this would be my answer to part 1, my moment around point O. Now, just for discussion's sake, let's go ahead and compute the magnitude of this moment using the Pythagorean theorem. We'd find out that MO is equal to 537.6 inch pounds. Okay, so once again, that's applying the Pythagorean theorem to those two components. So just to see what that would look like, this interactive actually has those numbers programmed into it. And so if I take that moment around point O, I end up with this MO, and can move things around here a little bit to see where that's sitting. You can see it's lying in that XY plane, right? We can look at it from the top and see it's coming over here with a positive Y component and a negative X component, which reflects the value that we found for that moment. And again, we could have also crossed F into O BXY and got the exact same moment. Okay, so one thing to pick up here is that in three-dimensional moments about a point, that we could end up with up to 3 dimensions of the moment around that point. And fundamentally what this point is, if you hold up your right hand, make it into kind of a thumbs up, curl in your fingers, point your thumb along that red vector moment about point O, your axis is your thumb, and the rotation goes in the direction of your fingertips. So essentially it says that this force is causing rotation around this axis, MO, with a magnitude equal to the 537.6 inch pounds. Okay, so that's spatially what this is saying. So moments are vectors, they're just a vector of rotation. So back over to our math, we want to compute part 2, which is the magnitude of moment of F around line OA. Okay, now there's two options for this. One option would be to take this moment around point O and then just dot it onto our line OA. I'm going to show the mixed triple approach. Okay, so this is going to be 2, we're going to do a mixed triple. And so in our mixed triple product, where we're still computing essentially the dot product of this moment around point O, we can set that up that our moment around line OA as a scalar value. Once again, it's a determinant. Now in the top row, I need to have the unit vector of line OA. And so let me go ahead and write this down below. So R of OA as a full vector is equal to, now this position vector ROA is going to have the same y component and z component of our position vector ROB, but it'll have a 0 in the x because it's not coming out in the x direction at all. And so the other two values here are 6.06 and 3.5. Computing the magnitude, ROA, can also write that as the vector magnitude. It turns out that that full vector has a length of 7. That was actually given in the problem. So then we can find that ROA hat, the unit vector, is 0.866, 0.5. Now, if these two values of 0.866 and 0.5 look somehow familiar to you, it turns out that they should be. This is the sine of 30, and this is the cosine of 30. We talked in chapter 2 how the unit vector components of a two-dimensional vector are simply the sine and the cosine of an interior angle of that triangle. Right, so we're saying here that fundamentally our unit vector, which this guy right here, this is our U hat OA, that its components are going to be the sine and cosine of 30 because it's defined by that 30-degree angle. All right, so back to our mixed triple. So we're going to put this unit vector in the top, 0.0 and then 0.866 and 0.5. Now a position vector, I could use the exact same one I used for my moment about point O, right? I'm going from my axes of interest to my point. Now I also, as an even simpler one, could actually go from A to B. Okay, so from A to B, this is going to be 12, 0, 0, right? So essentially what I just drew here is taking a position vector from A to B. So this is RAB, just like this is RAB. And then the force vector is the last piece, and so that gives me 0, 0, and negative 40. All right, so thankfully a bunch of different zeros in this computation. I still could compute this the same way if you wanted to by recopying the first two rows. So 0, 0.866, excuse me, the first two columns, 12, 0, 0, 0. So looking at these slants, there's a 0, there's a 0, there's a 0. Here's a non-zero coming back this direction. So that one is going to be non-zero and 0 and 0. Wow, one value that is actually going to be non-zero. And so it turns out, I'll scroll this direction, that my scalar moment of that force around line OA is equal to this 0.866 times 12 times negative 40, but it's the negative of that because it's a negative slant. We end up with a positive value equal to 415.68, and this is going to be in inch pounds. And I could compare this if I wanted to the value that I found of my total moment around point O. Okay, so of the 537.6 inch pounds, which is my total moment around point O, only 415.68 is actually directed around line OA, so hence that's the only amount of the moment available to actually loosen that bolt, because the bolt itself is along line OA. Okay, so this would be my answer. Just to rewrite this out, so M of OA is equal to this value, 415.68 inch pounds. So this is my answer to part 2. All right, so what we did here again, zoom out here just a touch, is we started by just kind of understanding, well, what's the problem asking? And we were asking for a moment of a vertical force around point O. Okay, I'm going to point an R cross F. And so this vector here is simply an R, and this turned out to be R of OB vector crossed with our force vector. Okay, so we found it had components, a negative in the I hat and a positive in the J hat, and we took a look at those in the interactive. We then said, well, how much of that moment is actually around our extension OA, or fundamentally around that bolt that we're trying to loosen up out of the block along line OA. And so what we did is we dotted that moment onto line OA. And if you wanted to check, you could dot basically this vector with this vector, and you should end up with the same value that we found right here. Okay, we're just doing this mixed triple is fundamentally just doing that dot product for us. Now, noting that in this version, I chose, instead of line OB, I chose this R to be R of OA. Now, I picked that just because it was a little bit simpler of a vector. It had more zeros to it, and it's still going between the line of interest to the line of action of that force. And so when we computed this numeric determinant, we found out that we were left with a value of 415.68. And so essentially around 80 or so percent of the moment around point O is actually going along that line OA, so it's useful for loosening that bolt. I hope that this is a useful example to you to get you think about how these moments about a line work numerically, and also why we'd want to use them in a physical scenario.